paper.
We have to draw a triangle to find out the angle in between here, here and there.
We're going to measure the angle here, right? Yeah, the angle there. So.
How would you check that it's actually 49? Trigonometry, so you could use the opposite and the adjacent length here to find out the angle.
Here, the ICT provides a stimulus for mathematical discussions.
So it's supposed to find length from A, B and C. That's going to be a triangle. That's a right angle triangle right there.
So now we've got all our lengths in our triangle. How will we work out the angle?
I think you should just go on the angle one and then just measure the angle.
Okay, super. Off you go. How would you check that this was the right angle?
Do like a rectangle.
Another line there.
Yeah. Segment.
Some pupils move on to work out the longest pencil that would fit into a square-based pyramid.
Oh, first we have to open it. How about this one? How about 3
Do we think that's going to be longer than maybe something coming down from the top?
Let me try. We predicted that the longest side is going to be from there, from one corner to the middle of the pyramid, which came up to 7.6. Now, what we need to do is just find the angle of it. So we're going to work it out using Pythagoras' theorem and then check if it's right.
Other pupils had true or false statements to investigate. For this, they would have to construct the 3D shapes for themselves.
It just means that we're trying to figure out if these statements are always true, or if they're sometimes true, or if they're never true. So you can use any of the documents we've used today, or you can construct a new shape yourself and try and investigate. You can start wherever you want.
The larger the volume of the cuboid, the larger the angle between the diagonal and the base. So we're just trying to make the cuboid now and trying to find out the angle.
So you make a diagonal between, let's use H and B, or E and C, right? The larger the volume of the cuboid, the larger the angle between the diagonal and the base.
So there's your volume. What else do you need?
And then extend.
You can actually make it empty. So now you can see through the shape and you can see your diagonal clearly here. The girls that are on the open-ended tasks that are working on the extension questions are doing really well with the investigating aspect. So they're using Cabri to kind of figure out if their ideas are right or wrong. The thing is, like that, when they can make the cuboid bigger and smaller at the touch of a button, it's something they could never work out with a pen and paper. They cannot see, you'd have to continually measure the volume, find the angle, make it bigger, measure the volume, find it would take forever. So I suppose they've come to a realisation really quickly.
As you make the volume even tinier, the angle increases. When you enlarge the cuboid, the angle begins to decrease. So this makes the statement false.
So how did the lesson go?
I think it went quite well. The students did really well with the software. I think they learned a lot about using geometry in 3D space. And I think the kind of approach that people normally take to that topic, students often going away feeling more confused than when they walked in. And I think these girls feel like they could tackle a problem like that, which is a real achievement.
I mean, what struck me particularly is that in the end, they're doing the same kind of maths in their books that they'd do if they just saw a static picture on exam paper.
Yes.
But they've seen something they can manipulate and move, so they've got an added experience.
Oh, absolutely. I think the whole thing about this is when students first meet any kind of maths, if they get a kind of an impression that this is confusing or this is difficult or I can't picture this, it tends to stay with them. And the girls today were able to take apart the shapes and manipulate things, and they really got the feel for what this is about. And although you mentioned they're using the same maths they would in essence use if they were looking at a 2D picture of this problem, they now understand why they're using that.
And I was thinking really about algebra and sequences, and thinking about how I can link together the many representations of sequences.
Jay's project involves using this handheld computer device to investigate quadratic functions and number sequences.
This function is x squared
What made you pick this particular topic?
Before he tackled the topic with his pupils, Jay and Alison discussed what usually makes it so difficult.
Quite often it's taught in different parts, and although students learn the square numbers sort of lower down in the school, they often don't look at the representation of quadratic functions until a couple of years later. And if it's being done by pencil and paper, by the time the students actually drawn all these out several times, they might have lost a sense of what this was all about. Whereas what we're doing today, they'll see the quadratic function plotted instantly on the ICT, and they'll be able to make those connections a lot quicker.
Jay then downloads the files the pupils will need from his laptop onto each of their handheld devices.
The number sequence we're going to look at first starts with the number 1. And the next number is the number 4. And the next number is the number 9. And then I've got the number 16.
Jay starts the lesson by setting out a sequence of square numbers and the corresponding patterns of squares. He then prepares to enter this sequence of square numbers into the computer software.
How many squares were there in the first one? Yes, Connor.
1.
In the second one, there were...
4.
4. Thank you very much.
9.
There were 9. Very good, very good. And in the fourth one, there were, going over to Matthew...
16.
16, thank you very much. So, that one represents 1, that represents 4, that represents 9, that represents 16. I'd like you to type them into yours as well and make sure that they're appearing on yours. That's fantastic. And you can put the fifth one in as well if you want to.
Jay's Year 8 pupils have used these handheld devices before to look at straight line graphs, but this is the first time they've encountered quadratic functions. Now, they're trying to find the graph of an equation that fits the points they've plotted.
You could put a square key and then you could put a number in there. 1. Enter. I pressed X, then I pressed the X squared button, then I pressed enter, and it just curved.
And let's think about this for a minute. If those are your X numbers, X squared becomes your Y numbers, and then you get a graph like that. OK?
Jay then hands out some other quadratic number sequences.
And you're trying to find what equation will go through the points that you'll get when you plot these values.
0, 3, 8, 15.
In your pair, choose one of the sequences, type them in, and
What should we do?
to see with the equation. So how could we get the equation with 1?
0.
You're right about
3,
that. Good points. Maybe later
8,
on. I'll do that.
15,
Sorry?
24.
So you're right what you're saying.
Enter.
We thought at the start we'd done the same as the last you know, I can't remember.
Last sequence,
Yeah.
which was x squared.
Yeah.
The equation was x equals.
But then when we done it, when we put x squared and we press enter, it's a bit off. So we thought, what could we do?
But
So
then we realised that every single number down here is 1 less than the squared number in the last one. So we thought if we put -1 at the end, it might give us the answer.
-1 here,
Sure.
and then press enter. It's on the line. We got it? Yeah.
What have you noticed? That it's just like add 10 in it.
Oh, it's add 10. So what was the equation we used last time?
X squared.
X squared. And this is, you just said it was...
Add 10.
So what do you think you might try?
X squared at 10.
Try it.
Yeah.
No.
This could be right. Oh, wow. Well done.
So we do 0, 3, 8, 15, and then we do 24. And then you press Control and Tab to go onto this part, and then that's the equation sign. So the equation would be x squared minus 1. Yeah, that's it. X squared minus 1.
What I'd like you to do now is just to pick one of the sequences you explored. I'd like you to draw for me the number pattern that goes with it. I'd like you to write down what the numbers are. I'd like you to sketch the graph that you got and write down the equation that you use. So all these 4 things here, 1, 2, 3, 4 things. I'd like you to write them down. They all represent the same thing.
Hey, write my name. 1, 2, 6, 7, 8, 9, 10. There's 1, 2, 3, 4, 5, 6, 7.
You've done 1.
OK, now, what have you found out today?
I found out that, you know, graphs, I thought it'd just be
Yes.
line, bar graphs, like pictograms and telegrams. But
Right.
this one is different because you're using square numbers. I didn't know that you could transfer, like, square numbers onto a graph.
OK, and what was special about the graphs that you got?
It's curved. All of them are, like, lines and stuff, but this one's curved.
That was something new for you. Fantastic. Did anybody notice anything interesting about how the graphs varied? So if you had x squared minus 1 or plus 5 or plus 10?
OK, if you did x squared, it would be low, but if you did plus 5, it lifts up and goes higher.
How high would it go then?
5 times more higher.
It would go 5.
Mhm.
OK. And if you did x squared plus 20, what would happen then?
It would go, like, lift up to 20, go 320.
And if you had x squared minus 1?
It would be minus 1.
Minus 1. Should we just have a
go
look
down.
at that on the screen? Because I'm not sure everybody spotted that earlier. What will happen if that was x squared plus 1 instead of x squared plus 10?
Where the curve is, it'll go lower.
It would go lower. And what number would it go through on the y-axis?
It'll go through 1.
It would go through 1. Let's have a look. So going over to my computer again and changing that. Change it to a 1. Oh, look, and you can just see that is 1, because there's 0, there's 5, and that's 1. OK, I think you've worked really well today, so we'll stop there. Thank you very much.
So what was Jay's reaction to the lesson and his pupils' work?
So much happened, really. What struck me as significant is that this was their first introduction to quadratic graphs, and they hadn't seen them before, and the fact that they were curved really came alive for them. They'd not seen curved graphs before, so that was quite fascinating. And had I done this on paper, it would have taken quite a long time to get those connections that we saw today, which is nice because the focus wasn't on the ICT, the focus on the maths. And so often people think of maths with ICT as actually being an ICT lesson when it isn't at all. It is a maths lesson. And when we asked them at the end what they'd learned, it was all about quadratic sequences. It was all about the shape of the graph. It's all about the fact that you can plot these things. It was all about the mathematics. And not about the technology, but technology was necessary for that maths to take place.